Hi guys, my name is Derek, and today I'm going to tell you about an intriguing innovation that looks to blend two technologies in a way that could improve the energy performance of buildings substantially. In this presentation, we will begin by going through a couple of key definitions, as parts of this presentation will be somewhat technical. We will then define the problem we are looking to solve with this innovation, and then give brief introductions to the two technologies that are being blended as a part of this innovation. Finally, we're going to go into the innovation itself and explain how it works. So starting by looking at those key definitions, the first one is R value, which is just a term for the measure of how well or poorly a given material prevents heat flow through that material. Higher is better in this case. The second one is PCM, which stands for phase change material. In terms of this presentation, it will be a material with the capacity to absorb or release large amounts of heat energy when going through a change of phase. An example of a change of phase would be going from a solid to a liquid form. Moving on to our problem, we're looking at the issue of building energy performance. Improving sustainability is a concept that is in the forefront of many of today's industries. Construction is no exception. One of the many areas within buildings that are currently being improved is the energy performance, which is generally defined as reducing the amount of electricity and natural gas required to operate the building. There are many rating systems and codes related to this today. They range from the well-known LEED rating system to the National Energy Code for Buildings, or NECB, which was recently adopted in Alberta. Even within the realm of energy performance, this is being tackled by many different disciplines in many different ways. These range from more efficient lights, appliances, and heating and cooling systems to more effective building envelopes to reduce the amount of heat and cooling that's required. The latter issue is specifically what we seek to improve with this innovation. Reducing the amount of heating and cooling required means a reduction of thermal transfer through the building's wall and roof. The three most common strategies for this are insulating, which significantly reduces the rate that temperature change transfers through a wall assembly. The second is mass wall or roof construction, which involves stone or other heavy forms of wall construction, which then absorb large amounts of heat, leaving the area around them cooler. These first two innovations will actually be combined in the innovation that we'll be getting to later. The third strategy is passive design, which, in super simple terms, involves the use of well-oriented windows and mass collectors, such as a heavy tile floor, to absorb the sun's energy and help heat the space during a cold month. There's a lot more to passive design, but we don't have time to get into it today. Now that we have a good understanding of the problem we're facing, let's have a look at the technologies that we can bring together to form a new solution. Insulated metal panels are lightweight composite exterior wall and roof panels. Usually they have metal skins and then they have an insulated foam core. They usually have very high R values per inch and are available in a variety of thicknesses and finishes. Usually they're designed to interlock in a way that the fasteners are concealed, which improves the architectural appearance. And these panels are already among the industry's leading solutions for improving building performance. Now that we have a concept for what metal panels look like, let's have a look at a technology that can be added to them to push their performance even further. PCMs, or phase change materials, are not new to the construction industry. In fact, studies of the use of PCMs in construction go all the way back to 40 years ago. They currently enjoy a growing popularity in the southern United States, particularly in Texas, where they're used beneath metal roofs to offset peak cooling hours. What is fairly new to the construction industry is the use of microencapsulated PCMs. Typically, these capsules are only microns wide, which is incredibly small. For reference, 1 micron is 1/1000th of a millimeter. Common materials used in the microencapsulation process include paraffin, fatty acids, or polyglycols. These materials are chosen because they have good properties for phase change within construction. The basics of a PCM is that when they are in solid form and exposed to heat, they will absorb a large amount of that heat and change phase to a solid. The reverse will happen when the PCM is in a liquid form and exposed to cold. As it moves toward a solid state, it will release energy in the form of heat. This absorption and release of energy is what we're trying to harness in construction to improve an assembly's ability to prevent temperature change moving through that assembly. The advantage of this heat absorption or release is only realized until the phase change is complete. This means that the furnace will need to kick in eventually, but it shouldn't need to run for as long, as the PCM helps to moderate the inside heat. The graph to the left shows how effectively a metal roof with a PCM material below it resists heat transfer when compared to a standard metal roof and asphalt shingles. We can see from this graph that a lot less heat is transferring through the roof with a PCM than any of the other two examples. Now that we have an understanding of both insulated metal panels and PCMs, let's get into the innovation itself. The majority of the elements shown in the sketch to the right are typical of metal panels. The key difference is that the insulation has been split in 3 layers to allow the PCMs to be put in between. The highlighted center panel will have a dimpled surface on both sides to allow gaps for the microencapsulated PCM to fill. As we're in Alberta, we'll use a cold weather example. During the winter, as the cold temperature moves through the outside layer of insulation and reaches the PCM will begin to change phase to a solid, and in the process release heat. This heat will warm up the area around it, slowing the rate that the cold temperature can move through the assembly. The same thing will occur once the second layer of PCMs is reached. Once the cold penetrates completely through the assembly, the furnace will need to kick in and will eventually revert the phases of PCM back to a liquid so the process can restart. Though this description likely makes this process sound fairly quick, by design it takes the PCM's relatively long period of time to completely change phase. In warm weather, the reverse is true, with the PCM absorbing heat as it changes from a solid to a liquid. This process can work in most climates, but is most effective in climates that are used to large swings in temperature in a short period of time. Texas, for example, where the days are hot and the nights, by comparison, are fairly cool, will benefit the most from the addition of PCMs to these panels. For more information on how the layers of the panels would be assembled, please refer to my prototype video. So now that you understand how this innovation works, why should we produce it? The biggest thing this innovation has going for it is from a performance standpoint, it has only advantages compared to other insulated metal panels. At a minimum, the product will provide the same performance as competitors, but with the PCMs, it will almost always well exceed those competitors' values. It also benefits from using existing installation strategies so workers are already familiar with how the panel should be installed. The largest disadvantage of this product would likely be its cost. Though there is the downfall that the PCM couldn't be serviced if it is performing poorly as well, this can be mitigated through rigorous testing and by providing a warranty on the panels. On the whole, I would say this panel is the perfect next step to the process of improving energy performance. Thanks for listening, and I look forward to hearing your feedback.